Swayam Prabha. Digital India. Educated India.
Welcome to Module 42 of Point-Set-Topology Part-I. So today we will take up study of properties of topological properties. So recall that we have defined a topological property by which something is true for one space, then it must be true for all spaces which are homeomorphic to it. Such a property is called topological property or topological invariant. Then we made a definition. This also I am recalling that a property is called smallness property if whenever a topology on a given set X has it, then all topologies tau prime smaller than that should also have the property. Similarly, a largeness property is one. Whenever tau has it and tau prime is a larger topology, then tau prime should also have it. Most of the topologies that we have, that properties that we have studied in this chapter, they belong to the first category, namely those which are smallness properties, except perhaps the first and second countability. They are not exactly of this nature, I have already told you. The next chapter will consider those which are likely to be called as largeness properties. Some of them, just like Hausdorff, some of like first and second countability, there will be some which are not exactly largeness properties in our definition. At present, what are the things they have studied? Like path connectivity, and all these things, right? So what we would like to do is look at a topological property for a space. Will it be automatically true for a subspace? Will it be true for a quotient space? If it is true for several of them, then will it be true for the product space? So these are the questions which keep bothering us. So we would like to do that in a systematic way as much as possible to begin with in one single place. Later on, we can't do all like that. As soon as a new topology comes, we can keep asking this question for that topology according to the time availability or our mood. Okay. And then there are many other kinds of questions also you can ask. Whether it will be persistent on taking closed subspaces or open subspaces instead of arbitrary subspaces. So there are modifications of such questions also. So this is what I mean by studying the properties of the topological properties. So let us tentatively make a few definitions. If we need more and more definitions or modify these definitions, we can keep doing that. First property is that hereditariness. So P is called, property P is called hereditary. If whenever X possesses it, all subspaces should possess the same property. it will be co-hereditary whenever X possesses it, all quotients of X should possess it. Similarly, a product invariant, there are three different versions here. One is finite product invariant, another is countable product invariant. The third one is product invariant without any qualifier. Okay, so that is most general. What is the meaning of product invariant? Whenever a family, depending upon finite or countable family of xi's are given, such that if each xi has a property, then the product should have, and conversely, if the product has it, each factor should also have it. Okay, sometimes people don't bother about this one. Whenever xi has its product has it, it's called product invariant. So the other one, they may call it as factor invariant. Once again, there are variants of these concepts. That's what I want to tell you. So depending upon the author and the concepts and what exactly you want to study and so on. Okay, there are variants. Like I already told you, hereditariness, instead of general things, you can just take open subspaces. You may call it open hereditary, or it may be true for only closed subspaces. Then you may call it a closed hereditary and so on. So they are weaker than actual being hereditary. So you may call together, they may call it as weakly hereditary. But then just weakly hereditary, there will be still ambiguity in this definition. Similarly for co-hereditary. Under any quotient map, if the property persists, then you may call it a co-hereditary. But suppose it is only true for open quotients, then you may call it weakly hereditary. Or some other people may call only closed quotients, then they may call it weakly hereditary and so on. Okay. So there are various versions of this one. So here is a table, okay, which will give you fairly good idea of whatever you are going to do right now, and a little more in this chapter 2, maybe in the next section and so on. So here I have listed 7 of the properties that we have studied so far: compactness, Lindelofness, first and second countable, separable, connected, path connected. Then these are the 3 properties of the properties that we would like to study: hereditariness, co-hereditariness, and productivity. Within productivity, there are 3 types I told you: finite productivity, countable productivity, and arbitrary productivity. So this being a little more complicated, we will do it next time. So today let us see whether we will cover this much. Okay. So what I will do, first I will take hereditariness for all these things one after another. Then we will go to co-hereditariness one after another. Okay. So let us look at compact spaces. You already know that closed interval is compact, but the open interval is a subspace, it is not compact. So compactness is not hereditary. On the other hand, you have also proved that every closed subspace of a compact space is compact. We have already proved such a thing, right? So that means it is weakly hereditary. Exactly same thing goes for Lindelofness also. Every closed subspace of a Lindelof space is Lindelof, right? Have you seen that Lindelofness is not hereditary at all? Do you remember when we have done that? Can you see it easily with some example? What is to be done? Take any Lindelof space so that there is a subspace which is not Lindelof. What is Lindelofness? Every open cover should have a countable subcover. Okay. A space which is not Lindelof, we have seen that. You can take, for example, an uncountable set and a discrete topology on that. That is the easiest example of non-Lindelof space. Okay. Now, instead of taking subspaces, you make this one in a larger space by putting one extra point, namely a Sierpinski's point. Okay. As soon as you put a Sierpinski's point, what is the meaning of that? That extra point, the only open set containing that point is a whole space. Therefore, when you take a covering, every covering of this space must have the whole space as one of the members. Therefore, that singleton subspace, the set, that will be the cover. You take just X member X, that's a cover. So it's automatically Lindelof. So this way it looks like as if we are cheating, but that's a legal example of a Lindelof space. Such a subspace is not Lindelof. You can cook up more pleasant examples or more unpleasant examples also if you like. Okay, so let us keep going. First countable and second countable. Okay. This is easy to check that both first and second countability are both hereditary. Let me do it for second countability. First countability you can do exactly same way. Take a countable base for a topology. Okay. Now take a subspace. What are the open subspaces of subspace? Take any open subspace in the original thing, intersect with the subspace. Suppose Y is a subspace of X. Now B is a countable base for Y. Take any member of B, intersect it with Y, and collect them, that will become a countable base for Y. That's all. Okay. So up till here we have come that countability and second countability are hereditary. Separability, connectivity, path connectivity, they are not hereditary. Connectivity and path connectivity you know already. Okay. You take an interval, remove a point, it's gone. The connectivity is gone, right? So subspaces are hardly need to be connected for a connected space and path connected space. But for separability, how do you do that? Why separability is not hereditary? Remember, separability is what? There is a
countable dense subset.
Countable dense set. When you go to subspace, this dense set may go away. That may not be in the subspace, right? But that doesn't mean that there is no other countable subset. So how do you give an example of a space such that the subspace is not separable? So perhaps you may try to do similar to this Lindelofness. Start with a non-separable thing and then cook up something bigger which is separable. No? That may work, no? So there are ideas you have to sometimes think about these things, right? So I have given you an example here. Remember, we had this semi-open interval topology in which the basic open subset were A comma B, A closed, B open. So this was left semi-interval, so RL on the space of on the set of real numbers. Okay. Consider semi-open interval, let's see. Okay. This is separable. You can check that. Namely, again, a set of rational numbers will give you a dense set. Okay, though this topology is larger than the usual topology. So this is a dense subset. So this is separable. Once you have a dense set in X, say A is a dense set, A cross A will be dense inside X cross X. So X cross X is separable. Okay. But now I look for a nice subspace here, namely the anti-diagonal, the line given by x plus y equal to 0. Okay. In the usual topology, this is homeomorphic to R. But in this separable in this semi-interval topology, in the product, what happens? This becomes a discrete space. Every point is open now. Why? Because given any point x comma minus x, you can take x plus x to x plus epsilon and minus x to minus x plus epsilon. Take the product. So this is half closed rectangle sitting on the point x. One of the corners will be on x comma minus x. Okay, so this rectangle, half closed rectangle will open. Its intersection with the line should be open, but intersection with the line is just single point. So all the single points are open. That means it is discrete. A discrete set with a uncountable set. A discrete topology and uncountable set, right? So that cannot be separable. Okay. This example is quite peculiar. I will use it again. Okay, in the next chapter. So as I have pointed out, connectivity and path connectivity, they are not hereditary. That's seen easily. Okay. Now let's go to co-hereditariness. Compactness and Lindelof-ness, we have seen that the quotients are also compact and Lindelof. Okay. If you don't remember it, you can just argue. Take an open covering for the quotient. Inverse image will be an open covering for the original space. Take a finite covering and come back. Okay. So that's it. So 3 and 4 are what? First countability and second countability, right? So these are weakly co-hereditary in the sense that if it is an open quotient, it's open quotient, then x is second countable implies y is second countable. Once again, it's very easy. What you have to do, start with a countable base for B, take f of B or B range over this curly B. Because f is open, fb is open here. First of all, that is the crux of this one. Now we can verify that this is a base for the topology on Y. So same thing works for local base at a point also. All right. So open quotients are preserving the first countability and second countability. So this is weakly co-hereditary. All right. In general, what happens? Once again, we have to cook up examples here. Okay. To examples, if you do it for second countable for the whole space or even for a point, the proofs will be more or less same. Okay, so I will prove it for now this time first countability. Okay, a space which is first countable, but the quotient is not first countable. Quotient means what now? General quotient, not open quotient. Open quotient will be first countable. Okay, all that I do is take infinitely many copies of R, disjoint copies. Is it first countable? Any first countable space, if you take any number of them and take disjoint union, it will be still first countable. The disjoint union doesn't disturb local properties. All right. So it's first countable. Now what I do, I construct a quotient of this by identifying all the zeros in each copy to a single point. So you can name them as R cross 0, R cross 1, R cross 2, R cross 3, and so on if you want. Okay, these are the copies of R, right? Now, 0 cross n, all of them will be identified to one single point. We denote it as 0. No other identification, this is all. Okay, so equivalence class is what? Whenever it is 0 cross something, it is equivalent to 0 cross that. All other points are singleton classes. So that is the quotient set. Give the quotient topology. What is the quotient topology? Something is open in the quotient space if and only if its inverse image is open in the disjoint union of all these copies of R. Okay. So that is my example here. X equal to disjoint union of Xn, countably many copies of R. And Y to be the quotient space obtained by identifying all the zeros to a single point. Then X is second countable, but Y is not first countable even. At that point 0, which is the class of all the zeros, okay, the first countability fails. Okay. So if it's not first countable, it cannot be second countable. So this gives you an example for both of them. Okay, how to see that it is not first countable? That is also easy. Suppose we have a countable base Bn for neighborhoods of 0. Okay, local base for this quotient space Y. Okay, let us tentatively denote this quotient space, quotient map from X to Y by Q. All right. Given any Bn, like B1 you pick up, then I can choose an interval in the X1 copy of R around 0, so that it is so small that this B1 intersection Q of X1, the image of that line, okay, that is not contained inside this Q of I1. Do the same thing for all n, B1, B2, Bn, and so on. You look at the corresponding Bn and then go to the corresponding copy of R. There you choose a neighborhood very small, so that that neighborhood doesn't contain this. That's all. Okay. So once you have got for each n, this interval in, you take u to be this disjoint union of all the in's in the disjoint union. Okay. When you take q of those things, that will be an open subset because the inverse image will be precisely disjoint union of these in's. Okay. So u equal to union of all these q ions, all right, that's an open subset containing the point, the zero, this zero bracket, the class of zeros. But because of the choice, this choice, none of the bn's will be contained inside u. Okay. If it's a base, then some bn must be contained inside u. For every open subset, there must be a point there must be a member in the base which goes inside that. Though this is not a base. In fact, what we have proved here is no neighborhood system, okay, can be countable, or take a countable set of neighborhoods, it cannot be a base. That's what we have proved. I started with countable, I never used that as a base. Countable set of neighborhoods of zero. Okay. Then I showed that it is not a base. All right. Once again, 5, 6, 7. What are they? Separability and path connectivity and path connectivity, right? Yeah. So separability is easily seen to be now co-hereditary. You see, it was not hereditary, but it's co-hereditary. Why? Take a countable set which is dense, go to the quotient, take the image, that will be also countable set. Claim is that is dense. Very easy, because all that you have to do is take an open set in the quotient space. You have to show that it intersects this image, right? Go to the inverse image. That is an open subset in X. So that will intersect the original dense set. That point will be in the intersection of these two in the image. That's all. Okay. 6 and 7, path connectivity we have seen that image, just the image of a continuous function itself has this property. Connected image will be connected, path connected, image will be path connected. So it's much more stronger than being co-hereditary. So the two columns we have seen, except a few things, one or two examples like this, we had all these things we had seen. So this is like a, this is like a summary of whatever we have done so far, except this example and this example. Okay. So now we come to the third column here, product. What we have seen is product of finitely many compact sets is compact. Have you seen that?
Yes.
But Lindelof space, one doesn't know. Finite is still true, but productivity as such, okay, means that it should be arbitrary product also. So here I am saying yes, but we don't have a proof for arbitrary products, not even countable products. Finite products we know. Similarly, for Lindelof, we don't know. Okay. The countability, first countability, again, finitely many copies it is. Even if you take countabilities, okay, But arbitrary product, we don't know. Okay. Similarly, second countability. The separability is more mysterious. What we have done is, for path connectivity, we have seen this one. Remember, path connectivity is easy. Connectivity also you have seen. Only for finite things we have seen, right? So partly many of these things we have seen, but we don't know all the full answers, none of them properly, right? So we shall take up this one next time. All right? So let's stop here.